Hey, this is a quick overview of Autochrome, the tool, and what it does. So let's just go over this diagram so we can kind of like have an understanding of what is happening in the tool. At the top, the input image is coming in. The rendering space generally is ACCG, but then we have to convert it to output sRGB because the research paper that turns the color information to a wavelength spectrum works on sRGB. It has a very narrow gamut that it actually works on the method that I'm using. So we have to convert it to sRGB. This this generates a wavelength spectrum, so something like this where you have like per pixel, you have a distribution like this. And then we can use the film sensitivity curves from different films and use that to kind of like mask out the individual emulsion layers. So we kind of like multiply those masks with the wavelength spectrum, and this gives us different emulsion layers. We can then use the CMFS and the standard illuminance to convert the spectrum to color. And so now we have our three layers in XYZ, preferably D65 space, but with OCIO, OCIO 1, the ACES configuration doesn't have that, so we're just going to use D60 for now, which doesn't line up with our CMFS curves, but that's a smaller issue. Um, the red emulsion layer, we're gonna turn that into ACCG because we have to apply halation on it, and halation doesn't really work on the XYZ color space. So we kind of make a mask and then apply a halation on that, and then turn it back into XYZ. And then we perform the grain synthesization, or however you say that, on all the three different layers, and then we can combine them all into the output image. So one thing to kind of note is what we are actually after here, these three different emulsion layers. These are the emulsion layers from film, right? And what we're using here as an input is kind of like the final, let's say, a CG render, right? It would be the final render that is has a nice distribution of like black to white levels, preferably like you would just kind of assume in sRGB space, we're in 0 to 1 space. But if we're kind of going backwards here, and this blue one is just an inverted version of the raw scan here that I have. So the first thing that is kind of like jumping out is that there's no pure blacks and there's no like pure whites necessarily. What that means is that our calculation for the grain, the stuff that is happening down here, um, what that is doing is it is trying to figure out the how much grain is supposed to be, or how many grain like particles are in a certain pixel. So a black pixel has 0 grains, and then a white pixel has as many corns of grain essentially that it's completely filled out, right? But the interesting thing here is we have nowhere is like an actual black value. So what that means, we're if we're using this as an input, we're gonna get some areas if it's completely black where we wouldn't have a single grain, which is not quite right. So ideally, we would want to work with this kind of like log space of sorts for the grain calculation, but this sRGB space for the wavelength spectrum calculation. And all of this is not quite set up yet, so we're getting a mismatch. For some things, this space is better. For other things, this space is better. But anyway, let's jump into the actual demo. Um, if you go to the README, you see some basic installation instructions. We can just run it with the Python by executing the module and passing the GUI flag, and that should launch the app very similar to the real Flare app. The user interface should be exactly the same, and it's kind of like the emulating that Nuke interface, so you should be familiar with that. If we pick an image here, I'm gonna set this to ACCG color space. Um, if you go to input here, this just gives you the input of the image, so you can kind of make sure that you're in that the color space and everything works. For the color space, right now I don't have support for OCIO version 2, so make sure that the ASUS configuration is OCIO version 1. Version 2 doesn't quite work yet. I have to change some things there. So that is one thing to keep in mind. And then the easiest thing is to just kind of like looking at this setup, going through the different steps. So the first step is going to be going from image to the emulsion layers. The first time this runs, by the way, you're going to see a model being calculated. You can open up the little viewer here, and it's going to take quite a while to generate the model. That's only the first time it saves it into your cache folder, and that should only happen the first time. Or every time you change settings, it generates a new model. The emulsion layers are red, green, and blue here. And as you can see in the green, for example, the green layer is not just the color green. If we go between red and green here, it actually has some like there's some green and some red values in the green emulsion layer. So what that means is these different emulsion layers don't map perfectly to our sRGB layers, right? They're not exactly the same. So that's why we're doing this whole ordeal, because we don't want to apply the grain per digital channel. We want to apply it per filmic channel, if that makes sense. So the emulsion here, uh, there's really not any reason to change this. The only thing that you can play around with is the curves file. The other stuff, as I said, this whole process of turning the color into wavelength, I'm working on that. It's not great. I can talk to you more about what's wrong and what doesn't work, but I would just leave all of these as is and only play around with this curves files. That way you also won't have to regenerate those models because it will always use the same model. Next we have this red emulsion layer. What happens with that is we can generate the halation for that. So if you go to kernel, this is essentially the kernel. It's just a convolve. This kernel is a GGX generated like specular highlight essentially. So the roughness slider kind of like acts exactly the same as roughness on a GGX BRDF. And then the height is just, you can think of it as the height from the film, how far that is away from the back panel. So how far the specular reflection would have, what the distance would be and how far it can spread. So the closer it gets, the smaller the specular highlight that gets. All of that, it's really simple. Essentially, like the larger this is, the larger the kernel is. It's just a convolve, right? That is happening on top of everything. So if we go to this halation tab, you can click on mask only, and then we can work on the threshold here, and we can kind of like bring up or down the threshold. So in case we only want the halation to happen on the areas in the red channel that were blown out and where light passed through the particles and reflected back on the blackboard. So we use this threshold for that. And then you can also do only halation only to see what the halation looks like. So if we make this kernel bigger, the convolve will make the halation bigger. So you have to go quite big for this to actually like be super glowy, if that makes sense. And it's not normalized yet, so the bigger you make it, the brighter it gets. And then if we uncheck that, we should have our halation. We'll talk about why this is kind of like working great a little bit later, but let's move forward to the grain. If you switch this to grain, now we're going in the next step here. And as you can see, the halation is causing problems because we're getting too bright and we're not normalizing the image. So I'm just gonna disable the halation for now. I'm putting it at 0. And that way we can work on just the grain without worrying about the rest. For the grain, the samples, and the blur signal. The blur signal is essentially just a filter value for the anti-aliasing. So 0 will get you no anti-aliasing, meaning you get pixels either having grain there or not grain there. And usually like half a pixel, I would say is okay, because anything bigger, you're really starting to blur out the image, right? Samples, I found anything above 1K samples doesn't really change. Then for the distribution, the grain mu is the size of the grain, so you can go to like 0.2 and you start almost seeing individual grain corns, so maybe 0.5, and here you really start kind of like seeing individual grains. So if you go to blue, these are the individual grains now that you can kind of see. The grain sigma, you have to be really careful. That is a randomization of the grain mu. However, it's absolute. So if you put a large value in here, it'll most certainly crash the render. I wouldn't even play with this. It gets really slow, and it's not great. Now the lift essentially is what I talked about here. That was just me playing around with it and seeing how that would affect it. Essentially what it does, it just lifts the image before applying the grain so that you don't get any black values. So it just takes this image and lifts it before it applies the grain, so that we're getting something a little bit closer to that for the grain calculation. Meaning in these really dark areas like this wheel well here, if it's at 0, for example, you might not get any grain there whatsoever. So, and if you go to just like 0.05 or something, lifting it, you start seeing some grain there. This is just me playing around with. Um, the lift was the easiest way, but ideally it would be some sort of a log curve that we could apply to it. Lastly, the resolution, that's just the output resolution, and then the device. I think you already are familiar with the OpenCL devices because you had to specify your own OpenCL device. That should be the same as in the old one. You actually should get a drop down here, so I have to check on that to select the OpenCL devices. And the rest self-explanatory. That's pretty much it. Now for the caveats in the emulsion one, or let's go to the input. So here's the problem, right? This white highlight, this is by the way a denoised image of the photo, so that's why it's a little bit weird. But this highlight here in sRGB is really just kind of like red at white, red at white at 1, green at 1, and blue at 1. But in real life, I would assume this white will probably be a really, 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 really bright red or yellow. I'm not sure how much blue there would be in here, right? So the problem here becomes that our emulsion layers, the emulsion layer it's kind of like the same throughout here. So our red layer is kind of like same, and then we have our green, we have even more in here, which is kind of weird, and then our blue also has a bunch of light in here. But I don't know if there's that much light in this sun highlight in the blue layer. So essentially what happens is highlights especially or just kind of like, yeah, I mean it's really highlights are treated as kind of like dissimilar as albedo textures and not as highlights. So that's the problem with the Jacob paper. It is meant for textures and not for outputs. That's where the machine learning models come in much more handy. Those treat highlights as actual highlights, and they can distinguish because they're trained on real data. That that's kind of like one of the biggest downsides right now of it all. Um, yeah, I think that's about it.